Magnetism and electromagnetism. It starts with magnetic materials. There are some materials which magnets can attract them. These are called magnetic materials such as iron, steel, nickel, cobalt. And there are some materials that magnet cannot attract. These are called non-magnetic materials such as plastic, wood, paper, or rubber. These are not non-magnetic materials. Look at this. These are non-magnetic materials that a magnet cannot attract. And these are magnetic materials that magnet can attract. Safety pins, steel nails, drawing pins, paper clips, needles. These are all actually magnetic materials. And look at this magnet. Magnet has two poles, north pole and south pole, and magnetic field or the magnet has greater strength near the poles. Similar poles repel and opposite poles attract. For example, a north pole and north pole, they repel each other, but a north pole and south pole, they attract each other. It's a very good demonstration. A magnet is suspended by a thin thread and another magnet is brought closer. So similar poles, when it is similar poles, they repel and opposite poles attract. Magnetic field. The field around a bar magnet is called magnetic field, or we can say the space, the volume of space around a magnet in which the magnetic strength works is called the magnetic field. How can we find out the magnetic field? How can we investigate the magnetic field pattern of a bar magnet? There are two ways. One is this one, and another one is this one. This one is that a bar magnet is covered by a piece of paper and sprinkle some iron fillings on the paper above the magnet. So we scatter iron fillings on top of the paper and we tap the paper gently. Tapping the paper, the magnetic field pattern appear like this. Magnetic field pattern appear that you can see in the diagram. And another process is that we put some compasses around the magnet, and the pointers of the pointers of the compass, they indicate, and these points are marked by pencil on the white paper, and then removing the compasses. After removing the compasses, join the lines, and the lines show the magnetic field pattern around the bar magnet. So in this experiment, we have to again place the bar magnet on a piece of paper. Many small compasses around the magnet we should place, and then we should just look at the pointers direction, and if we give dot by pencil on the paper and we just join them, we join the dots and we get the magnetic field pattern. So this is the magnetic field. Actually it is around a bar magnet. It's a very important diagram. We must practice to draw it. It comes in exam. And this magnetic field around a bar magnet, it has some properties that it shows the shape of a magnet, shape of a magnetic field. It shows the direction of the magnetic force traveling from north to south, and it shows the strength of the magnetic field also. So I repeat once again. That a magnetic field around the bar magnet, it has some properties and characteristics. It shows the shape of a magnetic field, it shows the direction of a magnetic force from north to south, and it shows the strength of the magnetic field. Remember, where the field lines are closer, the magnetic field is stronger, and where the field lines are further apart, magnetic field is weaker on that space. So we read magnetic materials, non-magnetic materials. We read about the bar magnets, south pole and north pole. Similar poles repel, opposite poles attract. And we have also seen the investigation to find out the magnetic field around the magnet by using iron fillings or plotting compasses. And now here we have seen the magnetic field lines. It has some features that it shows the shape of magnetic field. It shows the magnetic force going from north to south, and the blue lines you can see here, the blue lines, these are magnetic field lines. The blue lines are called magnetic field lines, and the direction you see here, the arrow, the direction indicates that field lines are actually from north to south. And here the field lines, the magnetic field is stronger, strong magnetic field present here near the poles, in both poles. And the magnetic field is actually weaker here because you see the gap between the magnetic field lines are greater. So these are some important properties about magnetic field and magnetic field lines. So overlapping magnetic field lines. What would happen if magnetic field lines overlap? Look at this. Two bar magnets, they are brought close to each other. North to south, there are field lines. North to south, field lines are going. North to south, field lines are going. North and North Pole, South and South Pole. Similarly, similar poles come closer, and there is a repulsion due to repulsive force. Look at this. In this area or in this space of volume, there is no field lines and there is no magnetic field at all because they repel. Similar poles repel, and two bar magnets are brought side by side, one after one. Look at the north to south pole, the magnetic field lines. Magnetic field lines are here. And south pole, similar poles. It could be south and south. It could be north and north. Look at this area. There is no field lines present here because they repel. Similar poles repel. And creating a uniform magnetic field. Uniform magnetic field has two properties. The field lines must be parallel and field lines must be equidistant. I can write it. There are two conditions for a magnetic field to become uniform. A uniform magnetic field must have what? The field lines must be the magnetic field lines must be parallel to each other. Magnetic field lines must be equidistant. All right. So please write down this note. Look at this. The field lines are parallel and they are equidistant. Then it can form uniform magnetic field. Induced magnetism. If you put a magnetic material such as iron nail or safety pins or needles inside a magnetic field for a long time, you see that that piece of iron nail or safety pin or needles, it behaves like a magnet. It behaves like a magnet. So magnetism induced into the magnetic material. I repeat once again, if we place a magnetic material such as iron, safety pin, needles inside a magnetic field for a long time, and then removing the instrument, the nail or the safety pin or the needle from that field, we will find that the magnetic material, it started behaving like a magnet, though the magnetic field strength of that material would be very lower or weaker, but it would behave like a magnet. And magnetic field induced means magnetic field inserted into the material, it's called induced. Or we can say that magnetism induced into the material, this is called induced magnetism. There are actually magnetic materials are of two types: soft magnetic materials and hard magnetic materials. Iron is a soft magnetic material because it lost the magnetism easily, and steel is hard magnetic materials because it keeps the magnetism for a long time. It keeps the magnetism for a while, and it's called hard magnetic material. Now we'll read electromagnetism. When there is a current in a wire, a magnetic field is created around it. This is called electromagnetism. Please underline. When there is a current in a wire, when there is a current in a wire, current flows through a wire, a magnetic field is created around the wire. This is called electromagnetism. That you can look at the diagram. Current is flowing through the wire like this, through this, and placing some compasses. The compasses pointers would point in a way that we can understand that there is a magnetic field. Or the wire is covered by a white piece of paper and sprinkle iron fillings. Iron fillings would give the magnetic field pattern. Magnetic field pattern will appear to show that there is really a magnetic field around the wire. And it can be described as right hand rule. Look at this. This is right hand rule. By using our right hand, we should grip the wire in a way that thumb indicates the direction of current, then finger curls the direction of magnetic field. Look at the magnetic field, the circular one. We said that when current passes through a wire, a magnetic field appears around the wire, and the magnetic field is circular one. You cannot definitely point where is the north pole or where is the south pole, as the magnetic field is circular. And just direction of magnetic field can be found by using right hand grip rule. Look at the diagram, figure 20.10, that how the person gripped the wire. Definitely when current is not flowing through the wire, then you can grip it, otherwise you may get shock. Grip the wire in a way that thumb indicates the direction of current. This is not a complete circuit. I can draw the circuit complete for you. For example, now this is a complete circuit. So current is coming from this direction, and is going through this direction. Current is going through this direction. And if you hold it here, just when the switch is off, and the switch is off, if you place your hand here, finger curls the direction of magnetic field. This is for a flat coil. Look at the flat coil. Look at the direction of current. This is the direction of current, the black arrow. The black arrow is the direction of current. And look at the magnetic field around it. So very important diagram for IGCSE O-level examination. And how can we increase the strength of a magnetic field around the current carrying wire? The magnetic field produced around the current carrying wire, how can we increase the strength? We can increase the current, and we can wrapping the wire into a coil called solenoid. Two things. Look at this. We can increase the current in a wire, and we can wrapping the wire into a coil or solenoid. A solenoid is actually a long coil. This is the question here, important question. How can you increase the strength of magnetic field around a current carrying wire? So these 2 points are the answers. We are increasing the current in the wire and wrapping the wire into a coil or solenoid. Solenoid is a long coil. Solenoid is a long coil. Now, what happens when current flows through a solenoid? Look at this. What would be the direction? What would be the direction of current? What would be the direction of current or the magnetic field when current passes through a coil? Right hand grip rule for poles define it. This is called right hand grip rule for poles. Look at this line. It's called right hand grip rule for poles. Grip the coil this way. Grip the coil this way. Finger, thumb. Thumb indicates the direction of north pole, where finger curves the direction of current. Now these black lines, you see the black lines, this is the flow of current. This black line indicates the direction of current. And you see the north pole and south pole, and this is a coil. So when current flows through a coil, thumb indicates the direction of north pole and finger curves the direction of current. This is called right hand grip rule for poles. And the strength of the solenoid can be increased by using the following procedure: increasing the current, increasing the number of turns of the solenoid, wrapping the solenoid around a magnetically soft core such as iron. Very important points. By increasing current, by increasing the number of turns, and wrapping the solenoid around iron, magnetically soft material. Why iron? Why not steel? Why iron? Because when you stop the current, the iron lost its magnetism. But if it is steel, when you stop the current, the steel becomes magnet permanently, or it holds magnetism permanently. That is the thing. That's why iron is a good option. And the question is that how can we increase the strength of a field around the solenoid? You can write the question here. How can you increase the strength of the field around a solenoid? So there are 3 ways: increasing the current to the solenoid, increasing the number of turns of the coil, and by wrapping the solenoid around a magnetically soft material such as iron. Now look at that. There are some question answers to solve here. Please open your textbook, page number 204. Which of these objects are made from magnetic materials? Steel nail, iron bar, and nickel coins. These are magnetic materials. Draw a diagram of two bar magnets placed so that two of their poles are repelling and attracting. Okay, explain you have drawn in the magnets this. So we can draw a bar magnets. Look at this, repelling. First of all, repelling. I can draw it here. Right here, in, and here also in. In and in. What does it mean? Repelling. Similar poles, they repel. And another diagram is attracting. Right here in, and right here is. Sorry, yes. Now opposite poles, they attract each other. Explain why you have drawn the magnets in these positions. The thing is that you have to write similar poles repel and opposite poles attract. What the three features of a magnetic field do field lines show? We have read it, right? One is shape, another one is strength, another one is direction from north to south. I repeat, shape of the magnetic field, strength of the magnetic field, and direction of the magnetic field from north to south. What is uniform magnetic field? A field which has the similar strength everywhere. In a uniform magnetic field, the magnetic field lines are parallel and equidistant. I repeat, a uniform magnetic field which has the same strength everywhere in which the field lines are parallel and equidistant. Draw a diagram of uniform field with between two bar magnets. So it's very simple. I can use like the side ones are a bit curved. This is north and this is south, and this is the south of this bar magnet, and this is the north of this bar magnet. Draw a diagram to show the shape of magnetic field around the solenoid. It is directly given in our textbook. I expect you to solve it. Draw the diagram by seeing your textbook. Better see the textbook and draw the diagram without seeing. How does your diagram show where the magnetic field is strong or weak? The magnetic fields lines on the where the magnetic field lines are closer, the magnetic field is stronger. The magnetic field is the strongest where the field lines are closest together. and weakest where they are farthest apart. I repeat once again, the magnetic field is strongest where the field lines are closest together and weakest where they are farthest apart. Question number C, explain what happens to the magnetic field if the direction of the current through the solenoid is reversed. So if the direction of the current through the solenoid is reversed, the directions of the magnetic field and its poles are also reversed. This is question number C. I repeat once again. If the direction of the current through the solenoid is reversed, the directions of the magnetic field and its poles are also reversed. Then we can discuss question number 5. Read it. In 1819, a scientist named Hans Christian Ørsted was using a cell to produce a current in a wire. Close to the wire, there was a compass. When there was a current in the wire, Ørsted noticed, much to his surprise, that the compass needle moved. Why did the compass needle move? Because a magnetic field was created around the wire when current passed through it. I repeat, why did the compass needle move? Because a magnetic field was created around the wire when current passed through it. Now, when there is a current in a horizontal wire, the needle of the compass placed beneath the wire comes to rest at right angles to the wire, pointing from left to right. In which direction will the compass needle point if it is held above the wire? Explain your answer. Okay, from right to left, the magnetic field around the wire is circular with the wire at its center. It therefore is in opposite directions on opposite sides of the wire. So better I write this answer. Number 5A, the answer B, magnetic field was created around the wire when current passed through it. Number B would be with the wire at its center. It therefore opposite directions on opposite sides of the wire. Would your answer to part B still be correct if the direction of the current in the wire was changed? Explain your answer. No, if the current actually is reversed, the direction of the magnetic field around it would be changed too. Right. So number C, I can write no current going through the wire is reversed direction of the magnetic field around wire. So if the current is reversed, magnetic field around the wire is also reversed. Question number 6, I want students to try by themselves. Please try by yourself.